Hello, and welcome back to Compressible Flow. I'm Professor Steve Miller. Today we'll be talking about my favorite and perhaps one of the most famous set of equations, the Navier-Stokes equations, and their particular derivation. This should be seen as a review for those of you who took compressible flow or aerodynamics. We'll try and do this in a concise and elegant way through, of course, the transport theorem. There are indeed more rigorous ways to derive the equations, but I think this one is indeed one of the most understandable. We'll then look at and review the derivation in both the differential form and the integral form. These equations are, of course, the basis of this entire class and the majority of the field of fluid dynamics in its subfields like compressible flow. Let's get started. The goals of our class are to seek mathematical models in the form of sets of partial differential equations that we can use to model and hopefully predict the fluid dynamics that we are interested in this class and others. Partial differential equations are sets of equations which, of course, are formed through a series or summation of partial differentials working on our field variables. Here, our field variables that we're interested in this class conform to those which come about from the conservation equations of momentum, mass, and energy. In particular, we'll typically deal with 5 unique field variables in this class. The first is density, which you can see is rho right here. So get used to, of course, Greek letters. And we choose rho because, of course, it's historical use. If you look up through the last few hundred years of research, almost everybody denotes density as rho. We do not so much seek mass directly, but we seek density. It is one of our unknown variables. The second, third, and fourth are, of course, the velocity components, or might just be written as a vector u. I made it bold because it's a vector. So u represents our velocity, and we can decompose that into 3 components in 3 dimensions. Our last variable comes from the energy equation, and we can have an energy equation for many different variables. And you'll see in this class we indeed solve for, say, enthalpy or temperature or pressure in terms of the energy equation. Here I denote E, capital E, as the total energy in this class. And we'll look for this type of equation in this specific class in the derivations. Even if we set and find and derive this set of beautiful partial differential equations, which might be called and classified as a form of the Navier-Stokes equations, we cannot find solutions of them analytically. And I'll mention this near the end of the class. We're also seeking compressible forms of the equations. We are not interested in incompressible form. There's nothing wrong with incompressible flow. It's just less complicated because, of course, you do not have to vary the density in the flow. And we'll define rigorously mathematically the density of these particular flows, that is, if it's incompressible or compressible. We cannot solve these equations analytically even today, except for very specific boundary conditions and initial conditions. And the solutions really have little bearing on practical aerospace engineering problems. We also have to make a large number of assumptions to find analytical solutions, and you should keep track of these relative to the governing equations which we develop today. For example, if we find particular analytical solutions across a shock wave in this class later on, you should know, of course, what the assumptions are. Otherwise, you might apply the solution and equations to a set where the assumptions are broken, and then you cannot expect to have a proper answer because the assumptions are broken and it does not apply. Naturally, we must also develop boundary conditions, just like you do for differential equations or partial differential equations, but here specifically for fluid dynamics. But we'll define these boundary conditions as we progress in the class later on. Let's look at these particular equations and their development momentarily. The important thing to remember here are the major field variables of density, velocity, and energy, and the other, perhaps, gas law that's required to close this system of equations. Even if we form these 3 major equations, we need a gas law to close it because we'll have more unknowns than equations. I like to start a lot of my classes with some quotes. Here are 2 which I selected by none other than Lucasian Professor George Gabriel Stokes. Let's read the first one and the second one together. He wrote, "I was capable of being moved mathematically, as it were, by the belief that a particular course was right. And I do believe that God put these views in my mind, working by means that which was in me to supply that which was wanting." Sometimes I wish people would write like this today, but you have to look at the context that he was indeed a Victorian. He was a high religious person, and these were his thoughts upon, of course, working in this field related to fluid dynamics. His motivation, of course, was looking at flows past spheres, that is, large spherical pendulum flows, in order to keep track of time and help define the units of time. This is why George Gabriel Stokes was motivated to work in fluid dynamics. Let's look at a second quote to get insight into the type of person who creates these equations. He wrote, "Then it is right that you should even now draw back, nor heed through I should go to the grave a thinking machine, unenlivened and uncheered and unwarmed by the happiness of domestic affection." This was taken in an excerpt from a 55-page essay to his future wife on why they should not be married. Indeed, he was a calculating machine, and he worked tirelessly in the field of mathematics, and that's why so many terms and equations today and methodology are named after, of course, Stokes. In particular, in this class, we look at the Navier-Stokes equations. Indeed, Navier probably did much more work on the equations than Stokes historically. Let's look at these two historical figures now. The first one, named after the Navier-Stokes equations, is Claude Louis-Marie Henri Navier. He was born in 1785 and lived through 1836, and indeed he was French. I do not know of an oil painting of Navier, unfortunately, and if you can find one, I would appreciate it. He was an engineer and physicist who specialized in mechanics, and today he's probably most well known for the Navier-Stokes equations. He worked and studied at the École Polytechnique, and then the École Nationale des Ponts des Chaussées, from which he graduated in 1806. In fact, he was really a civil engineer, and he constructed bridges, which some still stand today at a few different locations. He eventually became a professor of calculus, nonetheless, and mechanics at the École Polytechnique, which still exists today. And if you visit the Eiffel Tower today, you can look at the names which are engraved on it, and he is one of the names engraved on the Eiffel Tower. There's his statue today, so we have an idea of what he looks like. The second major figure in the Navier-Stokes equations is, of course, George Gabriel Stokes, which I just read from quotes from. He lived from 1819 to 1903, and indeed I don't ever believe that Navier and Stokes met. Of course, Navier was a Frenchman and Stokes was a British person, and we're pronouncing the name Navier-Stokes equations in America, in English, of course. So it's an interesting French-English-American pronunciation. He was a physicist, mathematician, and fluid dynamicist, and he worked in optics. And we know him from this class, from the Navier-Stokes equations. And he spent his entire career at Cambridge, where he became Lucasian Professor of Mathematics. Indeed, Isaac Newton held the same chair, and many other famous mathematicians, even today. He was the president of the Victorian Institute, and he is deeply religious and evangelical. And he rejected the idea of the Darwinian theory of biological evolution, which is unlikely a daring thing to say today. Nonetheless, he married Mary Susanna Robinson after a long amount of letters and paperwork and negotiation, who was the daughter of a reverend, and they had 5 children. Let's look at the mathematics through our view today of what they did. Of course, their original derivations are a little bit different, and in fact, they took many decades to come to the set of equations we know today as the Navier-Stokes equations. Let's make some notes about these particular equations. First, we'll assume that the flow can be represented mathematically, that is, the fluid flow, as a continuous transformation of 3-dimensional Euclidean space into itself. We look at the Navier-Stokes equations not as a statistical system of particles, for instance, but as a deformation of space. The space deforms, and of course it's driven by the conservation equations. And so we're not going to worry about gas kinetic theory. It is actually, these equations can be derived purely through, of course, topology. Now the transformation, as the flow deforms, that is, space is deforming, can be parameterized by a parameter t, which we'll call time. Little t will be time. And then we'll fix, through this deformation in Euclidean space, some rectangular coordinate system in our derivation. We'll call that x1, x2, and x3 because we're in 3 dimensions. And of course, you could derive this for higher order dimensions or lower order dimensions, 1, 2, or say 4 and higher, respectively. and will denote the particular point in space, a differential point of a fluid parcel, which is the smallest differential fluid volume, as a position by x. And so x will be a vector in space, three-dimensional space, and t is time. We'll then parameterize the position of a particle or fluid element or fluid parcel as p, and it'll move through the fluid from time t0 to some other time, in negative infinity to positive infinity. And so we define time and space in infinite dimension coordinate. Its new position will be another position x, as the fluid parcel moves from, say, t1 to t2. Now, x and t are, of course, related, the position of the fluid parcel and the time t. So we'll say that x is always determined, that's the position of the particle or fluid parcel, as a function of capital X, the new position, and t. And therefore, we can write x as a function of x of capital X and t, or the components of x for I equals 1, 2, 3 for a vector x, as the same function, of course, as the new position x and time t. Think about these definitions and remember them as we look at this mathematics. Now let's imagine that if capital X, that's the final position, is fixed and t varies, then the path of the fluid element or parcel must be specified in some mathematical way that's deterministic. It could be chaotic, it could be viewed as random, but it's certainly a deterministic set of equations, this deformation Euclidean space. So for some fixed time t, the equations that we might derive must determine a transformation of one particular region of space-time, initially occupied by a fluid parcel, into its new position at time t, a later time t. So assume that the parameterization is continuous and invertible. That doesn't mean that we'll deal with irreversible, reversible processes from thermodynamics, but we imagine that if this is a deterministic set of equations, then we can actually reverse the process, of course, and go backwards or forward in time, which is a property of determinism. And therefore, we can write capital X equals capital X of a function of the space and time, or the vector of the new position capital X as a function of space and time. A final assumption will be assumed that x sub I and capital X sub I are sufficiently smooth to differentiate. That is, whatever equations or solutions we find, they must have some property of smoothness, so they possess differentials. Now, based on our new position and original position, at capital X and small x respectively, we can define a transformation, which of course is the Jacobian. And if you aren't familiar with Jacobians, you should review them online. I'll try and also post a paper and some links on the class website. Here, the Jacobian defines the transformation. We'll call the Jacobian capital J, and capital J will certainly be a function of the new position and time t. Of course, that's relative to the old position. This can be written as the determinant of partial xi, partial xj. That is partial little x, the original position, with respect to the new position. I and j both vary from 1 to 3, and therefore this is the determinant of, indeed, a 3 by 3 partial derivative matrix. For example, in position 1, 1, we might have partial little x, partial big X. In position, say, 1, 3, for I equals 1, j equals 3, we'd have partial x, partial capital Z, or x sub 3. Now, indeed, the Jacobian from this determinant will be defined by definition as either 0 or positive real numbers. And you can see, of course, the determinant outcome is a scalar positive value for this particular matrix of partial derivatives. This defines the differentiable form of spacetime from one position, t, to the new position, say t new or t2. Now, we can define the material coordinate of the particle as x, its initial position. So we call the material coordinate of particle x its initial position. The spatial coordinates x will be referred to as the position or place of the particle at, say, time t. So the material coordinate, capital X, will be its initial position. which might be viewed as x. Due to the Jacobian transform, we have therefore defined some kind of relationship between little x and big X, which is the starting and ending position of the fluid parcel. And each of the hydrodynamic variables we'll try and express in terms of the material coordinates, which of course are a function of the deformation of the Euclidean space. And we'll introduce a function f for, of course, relating the original and new positions as little f and large f, respectively, which is, of course, written as the material coordinates. So we'll say little f of xt in one space and time of the fluid parcel is indeed equal to little f, and substituting x as a function of big X in t, which is written in terms of the determinant at time t, will reduce to be big F at big X of t. So we can write, as an example, the velocity u at time t of a particle initially at x through this particular definition through a simple differentiation. Let's say instead of f, we have u, which is its particular velocity u at time t, f u x t. You can see then, we can write big U with big X t. And now with our definition of the determinant of the Jacobian for this simple one-dimensional example, we can write u equals, of course, the ordinary derivative with respect to t of x of big X t will, of course, be equal to the velocity big U, with, of course, x equals xt, the same property. Now, capital X, remember, is the parameter which represents a given fixed particular particle. And this is the reason we use the ordinary derivative, but we really want to use partial derivatives. Now imagine that we have a velocity field. A velocity field is a field of vectors in space and time, which might be continually changing if we're interested in fluids. We'll call the velocity field u throughout this class. U is a function of x and t, and at 3 dimensions, of course, it breaks down into 3 vector components, as you learned previously in compressible flow, aerodynamics or fluid dynamics 1. If you don't recall vector fields, you'll have to review their properties which you developed in Calculus 3. And this is why Calculus 3, typically, which is a vector calculus class, where you study different surface integrals and volume integrals and their properties, is so important for fluid dynamics. Now we'll try and determine the principal transformation for solving the ordinary differential equation. So from equation 23 of the previous slide of this slide deck, we might write the ordinary derivative with respect to time of x of xt equals u of x xt with t, as we wrote in 23. Now remember, x with the large X with time 0 will be equal to x, of course, by definition. Here, x is our particular parameter, and we can therefore always write, like 25, implied by 24 and 23, of the ordinary derivative of some function f xt and partial t f of xt. We might ask, what is their relation? Well, here, of course, f and f are related. They're any one of the particular properties. We then might write 26. Here, on 25 left-hand side, we write d dt of capital F xt, which is, of course, the material coordinate, will therefore be equal to, according to 24, f d regular derivative, d dt of f of little x, capital Xt, t, arguments. We can then see that we can write the regular ordinary derivative as a partial derivative with respect to xi about dt, differentiating the function, say d dt of f, that's this term, with the same argument, with the derivative of xi dt, plus partial f partial t itself. And so we use the simple rule of calculus 1 to expand the second term of 26 into the right-hand side. This is a very interesting operation, and let's see what we can do with it. We can now see from 26 they can write 27. That is, the first term in 26, ordinary derivative of capital F at capital Xt, will be equal to the right-hand side, which we can write compactly using the material derivative operator, capital D dt of f of xt, which is, of course, the right-hand side of 26. And we can write that in box the equation because it's so important and fundamental to fluid dynamics. We can write the material derivative of f of xt equals the partial derivative of f with respect to t plus u dotted with nabla f of xt, which is exactly the right-hand side operation of 26. Please see if you can find the material derivative through these operations. There's other ways to do it which are maybe more physical, but this is a mathematical argument and way of finding it. We call this the material derivative of f in 28, which is one way to write our equations, of course. Here's one of the few theorems in the class. We'll say capital omega of t denotes an arbitrary volume that is moving with the fluid. That's the particular fluid parcel. We'll call it omega. That's the fluid parcel. And we'll let little f of xt be some scalar or vector function of position and time, which we can use to look at mass, momentum, and energy. The transport theorem, therefore, can be written as 29. And of course, there's a proof for this. The transport theorem says that the ordinary derivative of the volumetric integral of the fluid parcel of f of x and t is equal to the volumetric integral, which is denoted by the integral sign with capital omega of t dx. And the argument on the right-hand side is the partial derivative of f with respect to t plus the velocity vector with the inner product of nabla f plus f times the divergence, of course, u, which is nabla dot u in this case. So this is the transport theory. And through this theory, we will derive our other equations of motion. Let's look at this written in a slightly different way. We can write equation 29, the transport theorem, in this way. We can break apart the right-hand side into two volume integrals and write the second term on the right-hand side as a surface integral through, of course, the work of George Green and Odrogorski's theory of Russia. It states that the ordinary derivative of the fluid parcel of f, which is some function, either a scalar or vector field, will go as the volume integral of partial f partial t plus the surface integral of fu dot m ds. And of course, this volume to surface flux has the only change in the equation from 29. So we just modified the transport theory. But we define a new variable here. First, n is now an outward pointing unit normal to the surface of the fluid parcel, and we'll call that partial omega t, which you see as the surface integral operator with ds. S is the surface. And x is, of course, in this case, defined as the surface in this particular integral, which changes with time of the fluid parcel motion. So let's look at a particular simple proof of this. If you will consider a transform at some x of omega 0 to omega t, and x can be parameterized as a function of the material coordinate and time. Then we can write equation 30 as the following. The left-hand side remains exactly the same. The right-hand side then can be written as an integral over omega time t of f times the Jacobian, which we defined earlier in this class, which is, of course, equal to capital F and, of course, the same Jacobian. Here, of course, f of little x with a argument of big X is equal to f, which we showed earlier in this class. Now we can continue, and we can try and write the same left-hand side of 31 equals the ordinary derivative at omega 0 of fj dx, which is equal to, by moving that ordinary derivative inside and differentiating, the first term and the second term respectively. Now let's try and relate the integral of dfj at omega 0 to some omega at a later time. Remember our relation, of course, of the Jacobian and the partial derivatives. We can rewrite this term here as a partial f of x of big X plus u of x of big X plus nabla f of x of big X with the Jacobian. Using the definition of Jacobian and the relation, of course, of the material derivative, you'll see that indeed we can write at a later time partial f partial t plus u inner product of nabla f dx. All that really remains is to prove the so-called Euler formula. And this can be written as 34, which is d dt of j of big X of t is the divergence of u of x of big X with the Jacobian at big X. So you can see that the fluid, and here's one of the most important definitions in the entire class, will be incompressible for any domain or fluid parcel at time 0 and any time later t or negative t as this boxed equation. That is, the volume of the fluid parcel, or this little control volume as it deforms through space continuously, will be the same volume at a later time. And therefore, we might have a volume, and as it deforms in space, the volume in it doesn't change. So the surfaces might be moving the fluid parcels, being deformed by the fluid as it moves along with the deformation in Euclidean space, but the volume's constant. This is the most rigorous definition, of course, of incompressible flow. This is really a mathematical definition, and it's much more rigorous, that is, than just setting rho equals a constant. Now we can note from the transport theorem, and we can write equation 36. We might write that ordinary derivative of the volume integral at some time of f dx, which is some property, a scalar or vector field f, will go as, of course, the ordinary derivative of the same integral at time 0 of big F, j, replacing it and setting time to 0, will, of course, also be equal to, through distribution of the ordinary derivative through the interior of the integral's argument. And we'll have the integral at time 0 of the volume of the fluid parcel of df dtj plus f dj dt. Now let's just say we set now f of xt equals to 1, which is our choice, which will of course give us a flow based on the volume. This means the time rate of change, the ordinary derivative of the volume, that is omega at t, is equal to the ordinary derivative of omega at t, which is then equal to, if we bring it inside, as d dt of j dx. And so this is really another way of applying transport theorem to our fundamental idea that the volume of a fluid element doesn't change as the Euclidean space deforms if it's incompressible. Indeed, based on the Euler formula and the fact that the Jacobian must be 0 or a positive real value, and the fact that the arbitrariness of the choice of the domains omega and the initial domain 0, omega 0, that means that the condition for the fluid to be incompressible is necessary and sufficient if we write the divergence of u is 0 or nabla dot u is 0, which of course is the exact same statement. So you can see this is actually the so-called D'Alembert condition, which was derived and first used by Jean-Laurent D'Alembert in Paris before Euler set it out. And indeed, 38 is boxed because it's the equation, which is a mathematically less rigorous way of writing 35, which you applied in your previous classes. Since this class is called compressible flow, I would expect that you barely ever use or make this particular assumption. But now you know exactly where it came from in mathematical theory. Now we derived and developed our transport theorem and showed an outline of the basic proof of it. We will now study conservation of mass. Let's now define rho. Rho is our density in the fluid. It's a scalar, which we'll assume is positive, because of course we wouldn't have negative mass. But we define mass in terms of the density. We no longer think in terms of masses. We think in terms of densities, which is a mass per unit volume. But we define mass as a function of density, which is a scalar field. It changes in all space and all time. It doesn't matter how many dimensions we have, 3, 5, 10, 11, and time. we will define it as the mass per unit volume of the fluid at a single point x and time t. We then derive the mass from the density, as I show in equation 39. Here, m will be the mass at a single point in space-time, and it will be written as a volumetric integral over the fluid parcel of rho dx. And so this is a triple integral over the volume, of course, in x, y, and z in 3 dimensions, which varies as time. And so we finally define mass as a function of density. Now recall the principle of conservation of mass, which indeed states that mass of a fluid and material volume omega does not change as omega moves through the particular fluid. We can then write d dt of an integral of our fluid parcel at any particular time, integrated in volume, of rho must be equal to 0. Of course, you can see that this indeed will give us a constant like n39. So the time derivative of mass with respect to time should be 0. Simple. Now, using our transport theory, which we previously developed and shown in equation 30, let's just go back so you remember that, it's so important, right here. We can write, therefore, with density and substituting in the transport equation for f of rho and simplifying this simple equation 41. You should try this on your own. Let's look at 41 carefully to understand it. It's a volumetric integral at any particular time t of the partial derivative of density with respect to time plus the divergence of rho u dx will be 0 according to conservation of mass. Now, the integral can be performed analytically and we find 42. We'll have, of course, partial rho partial t plus divergence rho u is 0. So indeed, for this integral to be 0, the integrand must be 0. And that's why we're setting 42, the integrand, as 0. And therefore, we found a differential form, a partial differential equation involving the density rho versus time of the divergence, that's nabla inner product of rho u, where rho is density and u is the velocity field in space-time, and it's equal to 0 for conservation of mass. Absolutely important. The principle of the conservation of mass might be also expressed this way. We might write, for a fixed volume, we might write the ordinary derivative with respect to time of the integral of rho dx, which, as you know, is the mass in the fluid parcel, should be equal to the negative surface integral of the mass flux. Recall our definition of n is the unit outward pointing normal of our fluid parcel. And so this volumetric integral, the time rate of change of the density in the fluid parcel, is equal to the negative outward pointing mass flux. And this makes sense because if we have a fluid parcel, like a little box, and mass is leaving it, then of course the mass inside the box is changing. But we do not track mass, we track density. And that's why 43 is a density equation for the field variable density, of course. This can be written and interpreted as it's the rate of change of mass in a fixed volume omega is equal to the mass flux through its surfaces, which is the interpretation of 43 in words. We can also write 43 with a little bit more of a general formula. Notice the left-hand side is now parameterized with respect to time by writing, say, rho f dx is equal to rho times the material derivative of f dx, which is a perfect operation. So by moving that normal derivative inside the integral, we can write 44. Let's now move on to conservation of momentum. Now that we derived, of course, our most important 2 equations for conservation of mass, which is 41 and 42. And don't worry, I'll summarize these equations at the end of the class. Now, remember, conservation of linear momentum, Newton's law, essentially states that the forces acting on a fluid parcel in a continuous medium are of 2 particular kinds. And they might be viewed as external forces on the fluid parcel and body forces which act on the interior of the fluid parcel. So we can imagine our exterior forces will be written as surface integrals and our body forces will be entered as volumetric integrals on a fluid parcel. And we can use our transport theory to try and develop this particular equation. Here, in this case, F, our vector or scalar in the fluid space, omega, will represent a force per unit mass. and so we're normalizing against unit mass. It will then act on an element omega as the following, 45. So in some volume omega, we might have rho f dx, which is some force in this case. Now, the internal forces, like body forces, or the contact forces, like external forces, like pressures or shear stresses, will act on an element of volume omega through its bounding surface, that is, partial omega. So once again, let's define our outward pointing normal. N will be an outward pointing normal at any point on the surface of the fluid element, partial omega. And T sub n will be the force per unit area exerted by the material volume outside of partial omega. Therefore, the surface force exerted on the volume omega can be expressed by the following integral in 46, and look at it carefully. Here, Tn is some kind of forcing. Now in 46, we can write a surface force which is exerted on the volume omega, and it can be expressed in a general way. Tn must be some kind of forcing which is integrated over an area, per unit area. So that might be an example like internal stress of the fluid, like pressure. Now the Cauchy principle, named after the mathematician Cauchy, which we'll mention in a second, states that Tn depends on any given time and only on the position and orientation of the surface element ds. For example, Tn might be parameterized and written as an argument of x, t, and n. And so n is an important parameter or argument of Tn, because of course that's the orientation of the deformed fluid element as it transforms and deforms through space. The conservation principle of linear momentum states exactly that. The rate of change of linear momentum of a material volume equals the resultant force on the volume, written as and translated from the Latin of Newton in his Principia. We might assume that F is known. So using transport theory, we can write d dt of the integral of the omega, the fluid parcel of rho u dx, will be equal to its body force plus the exterior forces Tn, which we just defined. So you notice this is a surface integral and this is a volume integral for the body forces. And we wrote an equation for, of course, Newton's force on a volume in 48. Recall the formula previously developed. Remember, we related d dt of a volume integral of rho f is equal to the integral over the volume of rho times the material derivative of f. Look at the particular first term in 48 and 49. They are very similar, and so we can combine 48 and 49 and substitute 49, right-hand side, into the left-hand side of 48 and receive equation 50. Equation 50 is an interesting equation. It's an integral over the fluid parcel, volumetric, of rho du dt, material derivative with respect to u, is equal to the body forces plus the shear and normal forces on the fluid surface of the fluid parcel. And so this is one way we might write in a simple integral form of Newton's law. Now let's note some important facts about T sub n. It is in fact a vector, and it could represent the normal stress, which is expressed as a linear function of n in the following form in 51. We might write Tn as the normal vector which changes in x and t for the fluid parcel times capital T of xt. Capital T here in this formulation, it will usually represent temperature, but here we'll call it the stress, is a stress tensor. And so usually in three-dimensional fluids, it's a 3x3 stress tensor with components 1, 1, 1, 2, 1, 3 for the x faces with normal and shear forces in the y and z directions respectively. You should have written out this stress tensor graphically, of course, in your previous classes. It's a good time to review that stress tensor. Now we'll let LQ be the volume of the original fluid parcel, which might be a box at time, say omega, at time t. We can then divide both sides by L squared and let the volume go to 0 through a limit. And so we'll take, say, the surface integral of Tn ds divide by L squared, and let L1, that is, go to 0 by letting omega go to 0, the limit. And therefore, you can see that this reaches a limit of 0. And therefore, you might argue through this mathematical argument that the stress forces are always in local equilibrium. Now we'll let omega be a domain containing the fluid, and we'll consider a regular tetrahedron, perhaps, with a vertex and arbitrary point in X on the surface. And the three faces will be parallel in the coordinate planes. We'll let one slanted face have a normal, and that normal will be n1, n2, n3, and it'll have an area of capital sigma. The normals of the other faces on this tetrahedron will be negative e1, negative e2, and negative e3. And they'll, of course, have corresponding areas n1 capital sigma, n2 capital sigma, and n3 capital sigma. This is just basic trig geometry. We can now apply equation 52 to the family of tetrahedrons by obtaining and letting the limit of sigma go to 0, just like we did in the simple case, like in 52. And we'll arrive at the same type of equation. It'll be t of the unit normal plus n1 t of negative e1 plus n2 t e to the negative 2 plus n3 t e to the negative 3. And they'll all be equal to 0. Here, Tn will be equal to Tn, which is equal to Tn of xTn, and T of negative h will go as T negative h for some h being E1, E2, or E3. And of course, the normal is always greater than 0. So therefore, Tn can be expressed as a linear function of n. And we can now rewrite our previous Newton's law through the material derivative formulation derivative balanced by the boundary and internal forces. And we arrive at equation 54. We have a volumetric integral of the density times the material derivative of u dx equals a volumetric integral of rho f plus the divergence of the stress tensor dx. We can then once again integrate both sides. That is, the integrand of the left must be equal to the integrand of the right, or else 54 won't hold. And therefore we can write rho times the material derivative of u equals rho f plus divergence t. This is the heart of the Navier-Stokes equations. But we haven't derived the stress tensor t, which is another work. We can expand the left-hand side and expand the material derivative and write it in a little bit different form. We can write it as rho times the material derivative, which is in the brackets, of partial t of ui plus the sum from j equals 1 to 3 of uj partial ui partial xj. You can, of course, set I equals to 1 and write out the equation, I equals 2, write out the equation, and I equals 3, and write out the equation. And you'll have, of course, the momentum components conservation equation in the x, y, and z, or I equals 1, 2, and 3 directions respectively. The right-hand side remains, except now we write sub I and sub ji, comma j. Remember, each equation holds I constant for 1, 2, or 3, and the j's are summed from 1 to 3 in the equations. And therefore, we have a scalar equation from the vector momentum equation in multiple dimensions. It happens to be that equation 56 is actually the Cauchy equation of motion in differential form, which can be applied to many different fields, not just fluid dynamics. This equation, of course, was found, and the Navier-Stokes equations were simplified in many ways and brought to a modern formulation by Augustin Louis Cauchy. He lived from 1789 to 1857, and he was French. He wrote, "Very often the laws derived by physicists from a large number of observations are not rigorous, but approximate. Indeed, he was a contemporary mathematician living in a previous era." He was also a professor at École Polytechnique and indeed knew Navier as a colleague and fellow professor. He found in complex analysis, wave theory, mechanics, and elasticity. He was very proficient and wrote 800 articles and 5 textbooks. He was a royalist, and he fled France in the 1830 revolution and later returned, so he wouldn't be arrested and perhaps tried. Nonetheless, you can see one important equation in the lower right, which I hope you learned in a traditional aerodynamics class when you're doing contour integrals, complex integrals, which can be written as the summation of the residuals. This is an important theorem for calculating lift analytically from conformal mapped airfoils, and other types of aerodynamics problems. If these equations don't look familiar to you, I recommend you learn them, because of course almost all aerospace engineering students have learned them in one particular point in their careers. Let's return and continue with conservation of momentum. Now we still need to formulate T, the stress tensor, but it always depends on the type of fluid of interest, and that's why we left it as is for now. The simplest model of capital T, the stress tensor, might be just the contact forces acting perpendicular to the surface elements. So we might write little t of n, the unit outward pointing normal, is negative p of x of n. Here we introduce P as the pressure, and indeed P is defined as the internal stress of the fluid acting on the normal surface of the fluid parcel as it deforms through Euclidean space. This is what pressure is mathematically, and what we indeed know as pressure when we talk about it in our everyday lives. But here you see we've derived it and defined it through a rigorous mathematical approach. The minus sign is chosen so that, of course, when P is greater than 0, the forces on a closed surface tend to compress the fluid. So high internal stresses, that is pressure in a fluid, compress fluids. The pressure, and we'll call this static pressure P throughout the class, is exerted from an outside area on the surface of the element or fluid parcel. And so if you have some volumetric domain omega, it's outward forcing internal stress. Positive pressure will compress the fluid. Even fluids at rest exhibit internal stresses, which is known as the static internal pressure. For example, a fluid parcel will always experience a normal stress on or to itself. And indeed, this stress is independent of the particular fluid parcel's orientation. This is the idea of hydrostatics. And in your previous classes where you studied hydrostatics, this is how you might find the entire hydrostatic system, rigorously from the conservation of momentum equation and conservation of mass. Now we can write an equation for perfect fluid, which might have been found by none other than Leonhard Euler. Here in 58, we have written, indeed, the equation for a perfect fluid. This is sometimes called the Euler equations because it lacks viscosity. It's really the density times the material derivative of U equals the body forces times the density minus nabla P. The second equation, 59, we might write U dot nabla of Ui, which is the second term of the material derivative, as a summation from j equals 1 to 3 of Uj partial Ui partial xj for 1 to 3. So I've just written that out in Einstein notation for your convenience. You'll notice in Einstein notation, if you have, say, two indices, like j and j, that you would sum them from 1 to the number of dimensions of the fluid. So you can see these equations in the vector form or in the more compact form, which is written in Einstein or index notation. Of course, this was named after Albert Einstein. Now, all fluids, except perhaps some supercooled helium, for instance, exert tangential stresses across the surface elements. And of course, this is where Navier came in his famous analysis and gives him name in the equations of motion. He took, of course, the Euler equations and defined and derived the tangential stresses in the tensor T, which are independent of pressure. And so we can take T and write it as a summation of the internal stress of the fluid, which is the pressure, times the Kronecker delta function, plus capital P sub ij, which is the stress tensor, of course. In fact, we call Pij in particular the viscous stress tensor, where Tij is the stress tensor because it contains pressure as a summation of Pij. Now, delta ij is named after a mathematician named Kronecker, and Kronecker wrote out this form, and it has certain properties. Delta with I equals j is 1, and delta for I not equal to j is 0. And so negative p delta ij for I equals 1 to 3 and j equals 1 to 3 is a trace of static pressure in a 3 by 3 tensor, which is not a matrix. They have different properties. Now, Navier argued, and it's been mathematically proven for certain classes and wide classes of fluids, that Tij equals Tji, meaning that, indeed, the stress tensor is symmetric. Certainly we know the first term of the stress tensor is symmetric by definition with the Kronecker delta function, but Pij, of course, has non-zero off-diagonal stress tensor terms. And therefore, we can return to the Cauchy equation, which we just mentioned, and write out 61 by putting in, of course, a Pij type term into the stress tensor, which we write as Tij. And therefore, we can write partial t of rho ui equals rho fi plus tji minus rho ji ui, comma j. Here the comma j denotes that we're taking the partial derivative of this term in parentheses in the j equals 1, 2, and 3 direction. For example, for I equals 1, we would have partial tji minus rho ji for I equals 1 partial xj. So this represents, of course, operations of 3 partial derivatives written compactly in Einstein notation. The last term on the right-hand side is always put on the left-hand side traditionally, which of course is this term here, which is part of the material derivative left-hand side. So we talked about the momentum equations. The last conservation equation we need to talk about today is the energy equation. This goes to the first law of thermodynamics. Technically, the Navier-Stokes equations are the momentum equation and the conservation equation, which is some called an incompressible flows the D'Alembert condition. Let's concentrate on the third conservation equation, which we'll need throughout the class. The first law of thermodynamics will state that the increase of total energy in a material volume is the sum of the heat transferred and the work done on the volume. That's very important to remember. And you should have learned this in thermodynamics. If you don't recall this law, you need to review the class. Now we'll denote Q as some particular heat flux. And E will be the specific internal energy in this case, not E naught E. We can then find a balanced first law expression simply by writing out the volumetric and surface fluxes of the kinetic and internal energies, accounting for our stress terms. So look at the first term on the left-hand side of 62. It says d dt of the volumetric integral of rho of a half u squared plus e. So that's the change, the time rate of change of the kinetic and internal energy, specific internal energy in the volume. And it's equal to a body forces with respect to the volume plus the stress forces across the surface minus the heat transfer dotted with the normal on the volume. So we can interpret this like I've written on the bottom of 106. It says the integral, the first integral on the right-hand side, is the rate at which the body forces do work. The second term here represents the work by the stresses, which we just defined. And the third is the total heat flux into the volume. And that will be balanced, of course, by the change of energy in the volume at any one particular time t. Remember, omega is the volume of the fluid parcel, and partial omega t is the surface of the parcel. And so this is a mix of volume and surface integrals. Now we can write this equation using the same theorem of stress means and write F equals ui. And we can then use this term and rearrange through the use of the transport theorem, which we developed in this class. We can rewrite the left-hand side as d dt of the volumetric integral of rho of a half of u, which is kinetic energy, will also be equal to the volumetric integral of rho half material derivative of u squared is equal to the 3 right-hand sides, of course, is which the rate at which the body forces do work, the rate at the internal stresses do work, and the rate at which surfaces do work. Using the transport theorem and the Green's theorem, which you learned in your calculus classes, you might write 63 compactly as 64. Here we have the volumetric integral of rho times the material derivative of the specific internal energy plus nabla dot q, where q is the heat transfer, minus t colon nabla u, which is the dyadic notation, which of course is just t, ji, ui, uj. So this colon here is representative of this term here, which is nothing but the scalar product of 2 tensors, the stress tensor and, of course, nabla u, which is a vector. Now, we can compactly write 64 as 65 because, of course, everything in an integral must be 0 for this integral to be 0. Or it's a balanced equation which equals 0. And so since this is equal to 0, we can set it to equal to 0 and solve for the material derivative and put the other terms on the right-hand side. And so we have now rho times the material derivative is equal to negative nabla inner product of Q plus T dyadic tensor of nabla U. We'll go further with this energy equation 65 and make an assumption using Fourier's law, who we'll talk about later in the class as a historical figure. We arrive at 66. Notice the difference between 65 and 66. The left-hand sides are the same. The right-hand second term, the dyadic stress with, of course, gradient of U, remains the same. The second term is approximated with K, which is heat conduction coefficient, right here. And so we can write Q as, of course, K nabla capital theta, which is the static thermodynamic temperature. And through Fourier's law, we are able to introduce static temperature into our equations of motion, which will be used throughout the classes. But now you know how it appears in the energy equation and comes into the equations of motion and why it's so important in compressible flow. Now, we have found differential forms of the conservation laws of continuity, momentum, and energy. We also define the stress tensor, where it's T sub ij equals negative P, the pressure, internal pressure of the forces of the Kronecker delta function, plus capital P, which is, of course, the stress tensor, which due to viscous stresses. Now, viscosity plays a little role in the discussion of our class, and I'll try and leave this here, but I'll also post some material on the derivation of Pij. It's just out of scope for the particular undergraduate curriculum. Now, the first equation, remember, is a statement, a partial differential equation statement for conservation of mass in a fluid which is continually deforming. And we have never made the assumption of compressibility. The second equation is for conservation of momentum based on Newton's law. And the third equation, of course, is conservation energy with the Fourier assumption. Because, of course, you see the appearance of capital theta, which is the static temperature in the fluid. So these three equations, we have unknown variables, rho, U1, U2, U3, and typically we do not know capital theta, which is static temperature. And we also don't know P, the static pressure, which appears, and of course, in the stress tensor. So you can see we have one more unknown than equations typically. We typically specify the body force, of course. This is a problem. We also need to write the stress tensor. Thankfully, the stress tensor can be written in terms of the first and second coefficient of viscosity and the velocities of the fluid. And so there's no additional terms in Pij, which is what Navier did. What's important to remember here now is that we have to close these equations with a gas law. It might be, say, an assumption of ideal gas, and then we could write P equals rho RT. They would then have three scalar equations and one vector equation, and an equal number of unknowns in 2, 3, or even higher dimensions. We can also write these equations exactly in integral form, which we derived in this class. Once again, we have an integral form equation for 70, 71, and 72, which we can also apply in terms of Reynolds transport theory using the transport theorem, which you hopefully learned in your previous classes and will be using through examples in this class. Here, the integrals are all volumetric, and they're all over the fluid parcel at any particular time t, and the fluid parcel or volume is defined and it's shaped through omega. Notice we have not written these with its partial derivative form, and so we have a nice volumetric method. This is also an unclosed set of equations, this compressible Navier-Stokes equations, or so-called hydrodynamic set of equations. We indeed need to know one more thing, which is a gas law, which is another equation we set. Altogether, these are informally or formally, depending on your community, the Navier-Stokes equations. Indeed, today, the Navier-Stokes equations form the basis of a famous problem, and these are two screenshots in figure 37 in the slide deck of the Clay Mathematics Institute Millennial Problem. If you are able to solve this problem on this page and the next, you will indeed be awarded $1 million plus the Clay Mathematics model. Take a few seconds to read the slide yourself, but pay special attention to equations 1 and 2. They have appeared in this very class. Equation 1 is really the incompressible differential form in 2 or 3 dimensions of equation 68, the partial derivative equation, Navier-Stokes. But you see, in the clay mathematics problem, they have made the incompressible assumption. And so they are not even dealing with compressibility because, frankly, it's too hard of a problem. People can't even do the incompressible problem, let alone the compressible problem. The second equation is divergence u, or partial ui partial xi, is 0. That's just the incompressible, or D'Alembert equation, meaning the flow is incompressible, which of course is true if you look at equation 1 by definition. Here's the second page of the clay and math problem. If you find existence or smoothness of these equations, if you can prove existence of smoothness in R3, if you can show the solutions break down in R3 for some viscosities and properties, or if you can show the solutions break down given some properties, you will win the prize. Nobody has done this yet, and it's an outstanding problem that's been worked on for and since the derivation in Navier-Stokes. Today, we looked at the basic derivation from a mathematical perspective using the ideas of topology and deformations of fluids to find the full Navier-Stokes equations, and of course the energy equation, which is lumped in. We then showed and summarized the differential and volumetric forms of the equations. These will be the basis of the rest of the class. If you don't fully understand every step of the derivation, that's okay. I try to show the major steps and verbally discuss the steps in between. You can try some of these yourself, and if you have questions, of course, we can talk more in class. Thank you very much for your time today. I'm Professor Steve Miller.